To size the motor for lifting the elevator car, firstly, determine a load to be lifted. Calculate the weight of the elevator car itself and the maximum payload that the elevator car will carry. Secondly, calculate the required torque. The formula for torque is lift multiplied by gravity multiplied by lift height divided by the efficiency of the motor. Remember that gravity is equal to 9.81 meters per second squared. The efficiency of the motor is typically around 90%. Thirdly, determine the required power. Power equals torque multiplied by the revolutions per minute, or RPM, of the motor, divided by 60. Fourthly, select a suitable motor based on the power and torque requirements. Consider factors such as speed, duty cycle, and the operating environment of the elevator. To size the conductor to be used, firstly, determine the maximum current draw. Calculate the current rating of the motor based on its power consumption. Secondly, select the appropriate conductor size. Use tables from the National Electrical Code or other electrical codes to determine the conductor size that can handle the current draw while meeting voltage drop and temperature rise requirements. Thirdly, consider voltage drop. Ensure that the voltage drop along the conductor length is within acceptable limits to maintain proper motor operation. Fourthly, allow for future expansion. Choose a conductor size that allows for potential increases in load or motor size in the future. A riser diagram is a single-line diagram that shows the electrical connections and equipment for an elevator system. This includes the main power supply, the control panel, the motor contactor, overload protection, limit switches, emergency stop devices, interlocks, and wiring connections. To create a riser diagram, firstly identify all components. Determine the electrical equipment and connections needed for the elevator system. Secondly, draw the main circuit. Start with the power supply and connect it to the control panel. Thirdly, add the motor circuit. Connect the motor contactor and motor to the control panel. Fourthly, include safety devices. Add limit switches, overload protection, and emergency stop devices. Fifthly, interconnect all the components. Connect all components using wires or cables. Sixthly, label the diagram. Clearly label all components and connections for easy identification. The specific calculations and design considerations may vary depending on the type of elevator system, the load capacity, and the operating conditions. It is recommended to consult with an experienced electrical engineer for proper design and installation. For calculating the motor size more precisely, one needs to consider the total weight that the motor needs to lift. This includes not just the elevator car and its maximum payload, but also the weight of the cabling and any other components that are directly lifted by the motor. The formula to calculate the required torque is crucial. It's important to use consistent units such as Newton meters. The efficiency of the motor is a significant factor, which reflects how much of the electrical power is converted into mechanical power. An efficiency of 90% is a good starting point, but refer to the motor's specification sheet for the exact value. Calculating the required power takes into account the torque and the motor's RPM. This will provide the power requirement in watts or kilowatts. Selecting the right motor involves looking at the motor's power rating, but also its torque characteristics, starting torque, and overload capacity. Consider the type of motor, whether it's an alternating current induction motor or a direct current motor, and its suitability for the elevator application. Regarding conductor sizing, determining the maximum current draw accurately is crucial. This involves considering the motor's full load amps, or flow, from its nameplate. You also need to account for any additional loads that the conductor might serve. When selecting the appropriate conductor size, consult the National Electrical Code, specifically Table 310.15b16 for allowable opacities of insulated conductors. Consider the conductor's insulation type, its temperature rating, and the ambient temperature where the conductors are installed. Voltage drop is a significant factor in conductor sizing. The National Electrical Code recommends a maximum voltage drop of 3% for power, heating, and lighting circuits. Use the voltage drop formula to calculate the expected voltage drop based on the conductor's length, current, and resistance. To allow for future expansion, it's good practice to oversize the conductors by at least 25% to accommodate potential increases in load or motor size. This also provides a safety margin for unexpected surges or overloads. When creating the riser diagram, accurately identifying all components is essential. This includes the main disconnect switch, overcurrent protection devices such as fuses or circuit breakers, the control panel, the motor contactor, the motor itself, and all safety devices. Drawing the main circuit should start with the utility power supply. Show the service entrance, the main disconnect, and the overcurrent protection devices. From there, connect to the control panel, which houses the control logic and safety circuits for the elevator. Adding the motor circuit involves connecting the motor contactor, which is controlled by the control panel, to the motor. Show the overload protection device, which protects the motor from overcurrent conditions. Make sure to include all safety devices such as limit switches, which prevent the elevator car from traveling beyond its limits. Show the emergency stop buttons, which can be used to immediately stop the elevator in case of an emergency. Include interlocks, which prevent the elevator from operating if certain conditions are not met, such as the doors being open. When interconnecting components, use appropriate wiring methods such as conduit or cable trays. Ensure that all connections are properly terminated and labeled. Labeling the diagram clearly is crucial for troubleshooting and maintenance. Use standard electrical symbols and clearly label all components and conductors. Include wire sizes, conduit sizes, and voltage levels. Also, consider the grounding system for the elevator. Show the grounding electrode conductor connecting the electrical system to ground. Include equipment grounding conductors for all metal enclosures and equipment. The grounding system is crucial for safety and helps to prevent electrical shock hazards. When calculating the motor load for the elevator, remember to consider the duty cycle. Elevators typically operate intermittently, so the motor may not be running continuously at its full load. The duty cycle is the percentage of time that the motor is running versus the total time. You can use the duty cycle to adjust the motor's power requirements and select a motor that is appropriately sized for the application. Another important consideration is the starting torque of the motor. Elevators require a high starting torque to overcome the inertia of the elevator car and its load. Make sure the motor you select has sufficient starting torque to smoothly accelerate the elevator. Consider using a variable frequency drive, or VFD, to control the motor's speed and torque. A VFD can provide smooth acceleration and deceleration, improve energy efficiency, and reduce stress on the mechanical components of the elevator. Also consider the environmental conditions where the elevator will be operating. If the elevator is in a dusty or corrosive environment, you may need to select a motor with a special enclosure to protect it from the elements. For conductor sizing, remember to consider the ambient temperature where the conductors will be installed. Higher ambient temperatures can reduce the ampacity of conductors. Consult the National Electrical Code tables to adjust the conductor ampacity based on the ambient temperature. Also, consider the number of conductors that will be bundled together in a raceway or cable. When multiple conductors are bundled together, their ampacity needs to be derated. Consult the National Electrical Code tables for derating factors. When calculating voltage drop, use the appropriate formula for alternating current circuits. The voltage drop formula takes into account the conductor's resistance, reactance, length, and current. Make sure to use consistent units when calculating voltage drop. Regarding safety devices, limit switches are crucial for preventing the elevator car from over-traveling. Install limit switches at the top and bottom of the elevator shaft to stop the elevator if it reaches its limits. Emergency stop buttons should be easily accessible to passengers in the elevator car. These buttons should immediately stop the elevator in case of an emergency. Interlocks are used to prevent the elevator from operating if certain conditions are not met. For example, an interlock can prevent the elevator from moving if the doors are open. When creating the riser diagram, use standard electrical symbols to represent the various components. This will make the diagram easier to understand and interpret. Clearly label all components and conductors on the diagram. Use wire markers to identify the conductors in the field. This will make it easier to troubleshoot and maintain the elevator system. Remember to consult with an experienced electrical engineer for proper design and installation of the elevator electrical system. An electrical engineer can perform the necessary calculations, select the appropriate equipment, and ensure that the system meets all applicable codes and standards. In addition to the above points, it is also important to consider the following aspects when designing the electrical system for an elevator. Firstly, the power quality. The elevator system is sensitive to voltage fluctuations and harmonics. Therefore, it is important to ensure that the power supply is stable and free from disturbances. This can be achieved by using a dedicated transformer for the elevator system and by installing power line filters to mitigate voltage fluctuations and harmonics. Secondly, the surge protection. Elevators are often located in buildings that are susceptible to lightning strikes. Therefore, it is important to provide surge protection for the elevator electrical system to protect it from damage caused by lightning surges. This can be achieved by installing surge protection devices, or SPDs, at the service entrance and at the control panel. Thirdly, the emergency power. In the event of a power outage, it is important to have an emergency power system to keep the elevator running. This will allow passengers to safely exit the elevator car and prevent them from being trapped inside. An emergency power system can be provided by a generator or by a battery backup system. Fourthly, the fire alarm system. The elevator system should be integrated with the building's fire alarm system. In the event of a fire, the elevator should automatically return to the ground floor and the doors should open to allow passengers to escape. This can be achieved by connecting the elevator control panel to the fire alarm system. Fifthly, the communication system. It is important to have a communication system in the elevator car to allow passengers to communicate with emergency personnel in the event of an emergency. This can be achieved by installing a telephone or an intercom system in the elevator car. Sixthly, the accessibility. For elevators that serve public buildings, it is important to ensure that the elevator is accessible to people with disabilities. This includes providing audible and visual signals as well as braille markings on the control panel. Seventhly, the maintenance. Regular maintenance is essential to ensure the safe and reliable operation of the elevator system. A qualified elevator technician should inspect the elevator system regularly and perform any necessary repairs or adjustments. Eighthly, the codes and standards. The design and installation of the elevator electrical system must comply with all applicable codes and standards, including the National Electrical Code, the American Society of Mechanical Engineers, or SME A17.1 Safety Code for elevators and escalators, and any local building codes. Ninthly, the documentation. It is important to maintain accurate documentation of the elevator electrical system, including the RISO diagram, the wiring diagrams, and the equipment specifications. This documentation will be helpful for troubleshooting and maintenance purposes. Tenthly, the training. It is important to provide training to the elevator operators and maintenance personnel on the safe and proper operation of the elevator system. This training should include instruction on the emergency procedures and the use of the communication system. By considering these additional aspects, you can ensure that the elevator electrical system is safe, reliable, and efficient. Remember to always consult with an experienced electrical engineer for proper design and installation of the elevator electrical system.